Push record. All right. Go ahead. What's the problem?
F of x y equals y over 7x plus y prime.
What?
Yeah,
Plus?
all in the denominator. 7x plus y prime.
Y prime.
Like prime?
Yeah. Prime.
No, it's
Like this?
yeah.
Wow.
They want
Is this in directional derivatives?
I gotta see this.
number 5.
What the heck is that?
Might have smudge right here.
I think there's something on the screen.
No, that's a comma, dude.
No, it's real. Look, it's a moving smudge. It's very.
It's a comma, yeah.
Good job, Jay. Jay, you make me look like an idiot.
Good job, Jay.
Why is the comma at the top of the y though?
What?
It's just because it's saying
There's
there's
a
this
comma.
function and then there's theta. What are you doing with theta?
It's a little bit too far to the right.
Yeah, we're gonna go
Theta
ham
equals
on
negative pi over. We don't even need it now. No, you can do it anyway though. That'd be cool.
I don't care. Go ahead. Theta equals what?
Oh, negative pi over 6.
And we want to find the directional derivative of this function in the direction of negative pi over 2? Okay.
Oh, you're gonna give him the vector?
No, pi over 6.
No.
Oh, in the function of the direction. Oh no, it's in the direction of u equals cosine theta plus sine theta.
That could be important.
A little bit.
Cosine theta, sine theta. That's the unit vector. The theta is, tell me the theta
Pi
again.
over 6. Negative pi over 6.
Negative pi over
6.
6. Okay. Yeah. All right. So what we want to do is find the directional derivative of this function, y over 7x plus y, in the direction of theta at negative pi over 6. And what you're going to have to do to find a directional derivative is to find that unit vector in the direction we're talking about. The unit vector will have the form of cosine theta, sine theta. They give you theta is negative pi over 6. So the unit vector is cosine of negative pi over 6. What's the cosine of negative pi over 6? Square root of 3 over 2. It's totally correct. Okay, because we're in the fourth quadrant, and negative pi over 6 for the cosine's positive, and we get we get square root of 3 over 2. And the sine of negative pi over 6 is going to be negative 1/2. Very nice. So that's the unit vector. Okay? To find the directional derivative in the direction of our unit vector of our function. Now, do they give us a point as well, or we just have to find this in general? I guess in general. Okay, let's do it. What do you have to do here? Well, what it is a dot product, okay, of our gradient, del f, with the unit vector. The gradient is partial with respect to x. Okay, let's do this. All right, well, here, let me write it this way first, and then we'll do it out. And, and then this will be this. All right, so let's find the partial with respect to x. Well, that one's not too bad because it's, even though it looks like a quotient, y is going to be a constant. So we can consider the function this way. Okay, as long as y is going to be a constant here. So take the partial with this, negative y, 7x plus y, negative second times 7. So we end up with a negative 7y over 7x plus y squared. All right, that's the partial with respect to x. Partial with respect to y is a quotient rule. We can't get around it. So it's denominator, okay, derivative of the numerator minus numerator times the derivative of the denominator all over denominator squared. Oh, that's kind of nasty. What's that? The y's will cancel, so we'll end up with 7x over 7x plus y squared. Okay? So here's where we have our directional derivative in the direction of that unit vector for our function is equal to this dot product, negative 7y 7x plus y squared. 7x plus y squared. Dot, square root of 3 over 2, negative 1/2. Wow. Pain in the neck this is. Then multiply this, so we get negative 7 square root of 3y over 2, 7x plus y squared, minus 7x. 2 times 7x plus y squared. Well, that's kind of nice. We get the same denominator. So we end up with a negative 7 square root of 3y minus 7x all over 2 times 7x plus y squared. Wow. You could take a 7 out front, but it's not really going to go anywhere, or a negative 7 out front, but nothing else happens after that. That would be the directional derivative. Okay. Usually what they do is give you a point where you substitute in for x and y. Okay. But that would be the answer. Okay.
Can we do another one?
Yeah, we can do whatever you guys want. And then we'll do the space shuttle one. Oh, yeah. You all set? Okay. Dylan, you got another one?
Yep.
Go ahead.
Alright. So once you find the directional derivative again,
Mm-hmm.
the function at p in the direction of v, and the function is the square root of x squared plus y squared.
Mm-hmm.
The point is 724, and then the vector is 3i minus 4j.
All right, 3i
4.
minus 4j.
Yep.
Okay.
I don't know if I did that math wrong.
Well, let's take a look. So here, what do we have here? We've got a hemisphere. Okay. We got the top. Do we have a hemisphere? Okay. Z equals that. No, we don't. I'm sorry. That's wrong. Okay. Z equals the square root of x squared plus y squared. When you square both sides, you're going to get z squared equals x plus y squared. That's not going to be a sphere there. So you're going to get, this would be a cone. This will be a cone. That's what it's going to be. And we've got a point, 7, 24, 25. Because 7, 24, 25 is Pythagorean triple, right? 7 squared, 49, 24 squared, 576, 40. And we add that, is that the square root of 625? Yeah, I think it is. So 7, 24, 25, right triangle. So 7, 24, 25. We've got a vector 3, negative 4. 3, negative 4. We're pointing back this way. And we want to find the slope of the tangent line of the curve that's produced by taking our surface, intersecting it with a plane containing this point in the direction of 3, negative 4. Back that direction, okay? 3, negative 4. So whatever that is, okay? It's going to give us a curve that looks like this. And the slope of the tangent line is going to be off this way somewhere. That's what we're doing here, okay? That's what it's doing. We're finding the slope of that tangent line in that direction. Well, let's do it. What do we need? We need the partials. X squared plus y squared to the 1/2. Partial with respect to x, 1/2. X squared plus y squared, negative 1/2 times 2x. 2's cancel. We get x over the square root of x squared plus y squared. Partial with respect to y. This to the 1/2 is 1/2 x squared plus y squared to the negative 1/2 times the 2y this time. Get y over that square root. Okay. the directional derivative in the direction of our unit vector, which they give us, kind of nice, at this point, well, let's do it for x, y first, and then we'll substitute in for x and for y, is equal to the dot product of our gradient with our unit vector. The gradient is x over square root of x squared plus y squared. Okay. Y over square root of x squared plus y squared. Dot 3 negative 4. So multiply this out. We're going to get 3x over that square root minus 4y over that square root. And that's 3x minus 4y over that square root. That's the directional derivative. What we want to do is take the point 724. So we're going to take 724. And we're going to get 21 minus 4 times 24, 96 over 25. The square root of 7 squared, 49, plus 24 squared, 576, is 625, 25 squared. Okay, like I said, it's a Pythagorean triple. It's not one that's well known, that 724, 25 one, but Pythagorean triple. So we get an answer of, wow, negative 75 over 25, which is a negative 3. Holy mackerel. That's pretty cool. So the thing is actually pointing down this way. Try negative 3, Dylan. But when it comes out that nice, you got to believe it's correct. What? You serious?
Web sign's wrong.
No.
You probably just like didn't use some kind of crazy notation.
You ever put like -2 or something?
I
Wait,
did the negative 3.
negative 3. Let me see.
Like, that looks like a negative 3 to me.
Is there like some kind of notation?
I don't know. Like,
So I think it has to be in vector notation.
No, the directional derivative is a slope. It's negative 3.
I have to make it slope.
We could do practice another problem and compare the
Yeah.
solutions.
You want me to do that?
What do you want to do?
Do it right now.
Are you doing it?
Oh yeah.
It's the only
Wait, I
way.
don't see anything. This, wait a second. 7, 20, 7, 24,
Love a sign
25.
No, it's just a number.
It's a number, yeah.
Yeah. Do we?
We just
What
go-
the heck is wrong with that?
we go-
Let me check my math here. 3, negative 4. Did we do 3, negative 4? We did that right? Yeah, it's 3, negative 4. All right, let's check it out. This to the 1/2, this, negative 1/2 times
This is good,
2x.
'cause I have one more submission left.
And the partial with respect to y, 1/2, this, this cancels, this cancels. Unit vector is 3, oh, that's not a unit vector. It's not, 3 negative 4 is not a unit vector. 3, yeah, we gotta make it a unit vector. I thought that was the unit vector. All right, the unit vector is this divided by 5, and this divided by 5. Okay, we didn't divide by the magnitude. I thought, I should have caught
That
that.
was my fault.
No, Dylan, I should have caught that. Totally me. It's mine. It's mine. All right. Yeah, we need a unit vector. I thought that was the unit. I should have known it wasn't. But okay. So 3/5, negative 4/5. So here we go. 3/5, negative 4/5. All right. Let's. So that all that does is makes this with a 5 here and a 5 here. So we get a 5 down here, and we get times 5, and we get a 5 down here. So I think we should get a negative 3/5 out of the whole mess.
I got it. Don't even try it.
Try a negative 3/5. I think that's all that happens is the 5 just carries all the way through.
There you go. Yep.
Yeah, baby. I mean, yeah.
Thanks, brother.
All right, good deal. No problem. All right, good deal. Okay, any others? Well, I'm going to do the space station problem, and I know he's not here today, but I'll have the notes for him, and I can go over it with him. Here's the problem. We're going to. Oh wait, we got time. Max-min problem,
Okay, so
and the situation is this. The International Space Station rents out space in the station to companies who pay big bucks to put some space on it, or they run experiments or do whatever. Let us suppose that we have rented out this space, and this space is formed by the corner of the room here with a plane that comes down this way. Okay? What we have here is a tetrahedron here. Okay? Got a plane that comes through here, and we've got this space for our company to run an experiment. And what the experiment entails is putting a tank that's in the form of a rectangular solid in this space. Okay? It could be some kind of tank filled with water. We're doing an experiment with mating habits of lobsters. That's what I sometimes use in zero gravity space. Okay? We want to maximize the volume of the tank that we can put in that space. But that tank has to be anchored, okay, at the corner here. The opposite vertex of the tank has to be anchored here on that plane that's coming down. Okay? And given those constraints, here, let me draw this thing. Here's what we have.
Why do they use such an archaic shape for the space they rented?
What's that?
Why do they use such an archaic shape for the space they
Well, it could be that somebody else has rented out the space in the room and needs this part of it, needs this diagonal plane, and so you got this little bit of space left out. I don't know what it is. I'm not sure, David. I'm just, yeah, just a messenger here. Here we go. Let's suppose that our space, let's suppose this is 12 feet high. And let's suppose along the x-axis we have 9 feet. And let's suppose along the y-axis we have 6 feet. That's the space. That's our tetrahedron right there. And what we're going to do is put our rectangular solid in here. Okay. Okay, wait a second now. Make sure I'm doing this right. Okay, like so. So that this one vertex of our solid is anchored right at the origin, and the opposite vertex here is on this plane. Okay? We need those two anchor points. Okay? And what we want to do is maximize the volume of that rectangular solid inscribed in this tetrahedron. Okay? So let's call this point right here X, Y, and Z. So we want to find X, Y, and Z so that the volume of that tank is maximized. Well, what is the volume of that tank? What is it that has to be maximized? What is it?
XYZ.
XYZ. That's the quantity to be maximized. But there's a problem here. The problem is we have 3 variables. And what we know is, in order to solve the problem, we need to cut this from 3 variables down to 2. We need to take advantage of some other piece of information, a constraint imposed by the problem itself. Can anybody figure out what kind of relationship between X, Y, and Z that we have here that we can take advantage of to eliminate a variable?
set it equal to different than like what the W?
Well, we need something different, something that I haven't taken advantage of yet. And that is the fact, well, let's have you think about it first.
The ratio?
Not really. Dylan?
Can you do something with the parameters of x, y, and z on that type of adhesion and like use a triangle?
Okay, but so this point right here, and what are the coordinates of this point, by the way? This point right up here? What would be the coordinates of this point?
X, Y, and Z.
X, Y, Z. And what about that point? Where is it?
On the plane?
It's on the plane. That's exactly right. It's on the plane. It's coming down here. That point X, Y, Z is on the plane. So if it's on the plane, there's a certain constraint imposed by the equation of the plane. We need to find the equation of that plane. Well, there's a trick here. Okay. There's a trick with linear equations. If you know the two intercepts, let's suppose you know the y-intercept of a line is 0b and the x-intercept is a0. Do you know the equation of that line right off the top of your head? Here, I'm going to just show you this here. It's kind of interesting, I think. So you have this, and you have a line that comes down this way. Oh, by the way, STCC math team at this moment, this instant, as I speak, is #1 in New England right now.
Hell yeah.
Right
Wait,
now.
really?
Right now, yeah. Some of the results are in from a few of the schools. Not very many. But some of the schools are sneaky. What's that?
Those two are holding it down. They had two of the higher scores.
Yes, they did. Yes, they did. Our two best scores right here next to each other.
I think it was higher.
But I'm just saying that at this moment, we are #1 in New England. At this moment.
Give these guys a golden calculator award.
Teddy, we didn't make the cut.
Almost.
This moment.
We're close to the cut. Like, if we didn't guess,
That'd be
I know.
Did you say that because there's a similar question that was on there like this?
I tell you why I said that. You know why I said that, Liam?
Because I remember this question.
Because this little trick, and I was thinking to myself, people on the math team should know this little trick of the intercepts. And then I thought math team, and that's why I did it. But there was one like this, wasn't there?
Yeah.
Yeah.
You had to find what the intercept, of course, the intercept would have been.
Yeah. Well, that could have played a role in here too. Here's the deal. If you have a line, 0b, a0, the equation of this line, okay, is x over a plus y over b equals 1. Okay? That's true. For any line having, as long as you know the two intercepts, you immediately know that the equation of the line. Let y be 0, x is a. Let x be 0, y is b. You get the 2 points. This is the equation of that line. We got a plane here. We've got the 3 intercepts. That same little trick works for the equation of the plane. X over 9 plus y over 6 plus z over 12 equals 1 is the equation of that plane. So that eliminates the need for finding this vector, crossing the two vectors to get a normal vector, then using the normal and a point to find the equation of the plane. Just by knowing the intercepts, we can write it immediately, okay? Instead of having to do all that cross product stuff. Now, I want to put this in, I want to solve for z because I'm going to eliminate z. So let's solve for z. So z over 12 is equal to 1 minus x over 9 minus y over 6. Let's multiply by 12. Z is equal to 12 minus 12x over 9, that's 4x over 3, minus 2y. That's unfortunate, isn't it? But that's the way it goes. So there's z. We can eliminate z. So v is equal to the volume we wish to maximize, xy, 12 minus 4x over 3 minus 2y. And I'm going to multiply it through. So we get 12xy minus 4x squared y over 3 minus 2xy squared. That's the quantity to be maximized. Now, any thoughts on this before I continue? Should we make it a cube, for example? Do you think that would be the way to go? Or not? Right off the top of your head, any feeling for what we should do here? You know, if the plane were intersecting at these 3 points were the same, say 6 here, 6 here, 6 here, there's no doubt in my mind a cube would be called for, okay, as more efficient. But because this is 12 and that's 9 and that's 6, you might think we should take advantage of the fact we have more height up here and stretch that thing so it's higher this way and a little bit longer this way, and this would be the shortest side, okay? And that's indeed what happens here, okay? If everything equal, make it a cube. I'll tell you what. Let's suppose you had no restriction on the shape. It didn't have to be a rectangular solid. What shape would you use to make sure that you enclosed a maximum volume in that tetrahedron? You would use a what? Oh, you? Wow. What an awesome, yes, you guys are totally right. Of course, you used the whole thing. Absolutely. All right, let's forget that. Okay, here's the deal. That's pretty interesting. Let's suppose you had a choice of 2 shapes, a sphere or a rectangular solid.
Probably sphere.
Probably a sphere. And you know what happens here? It's kind of interesting. If the things are more or less equal, a sphere is the way to go. But as you stretch one side out, it turns out that the rectangular solid is better than the sphere.
I would go rectangular solid because, you know, your charges are symmetric to your field shape. So.
Well, this sounds like a physics problem.
Yeah.
Yeah.
Physics is thinking out of the box.
Yeah. All right. But anyhow, it's really kind of interesting because at some point, there is a point when the two are exactly equal. The volume of the sphere and the volume of the rectangular solid so inscribed is pretty interesting.
They'd like the charge density inside that sphere.
It's okay. We don't do physics here. All right.
Thank God.
I know.
Oh, man.
Okay.
Thank Burns.
Same thing.
That
Same.
stuff's,
All right.
that stuff's fine.
So the volume we're trying to maximize is this one. All right, well, here we go. Let's go through it. It gets a little messy here, but we can do it. Well, what do we do to maximize this volume? We need to find critical values. Okay? We should also recognize what the endpoints are. Let's do that first. X is from 0 to, what are the constraints on X? 0 to 9. The Y's are going to go from 0 to 6. And the Z's from 0 to 12. But it turns out at any of these endpoints, we'd end up with a volume of 0, so we don't care about the endpoints here. Endpoints will give us minimums and not maximums. It's the maximum we're looking for. All right, so what do we have to do here? We're going to find the partial with respect to x to find critical values. 12y minus 8xy over 3 minus 2y squared. We're going to set that equal to 0. Take the partial with respect to y to get 12x minus 4x squared over 3 minus 4xy and set that equal to 0. Check these out. Make sure I don't make a mistake here. One mistake and we're dead. All right. In the first one, we're going to factor out a 2y to get 6y. No, geez. Get a 6 minus a 4x over 3 minus y equals 0. And the second one, I'm going to factor out a 4x to get a 3 minus x over 3 minus y, I think. Okay. Yeah, is this okay?
Yeah.
Okay. Now, we want to find x's and y's that cause both these partials to be equal to 0. Clearly, if y is 0 and x is 0, that's a critical value. We don't care, okay? Because x and y equals 0 give us a volume of 0. If y is 0 and x is not, if y is 0, this y is 0 here. Also a critical value would be when x is equal to 3. Because then if y is 0 and x is 3, no.
Equals 2.
I'm sorry, that would not be good. It equals 2, and that's not what I want. What I want this to do is be equal to 0, so x is 9. So if y is 0, x is... All right, so here we got for critical values.
9, 0.
Yeah, we got 0, 0 is a critical value, okay? We've got 9, 0 is a critical value. Now let's let x be 0, and if y is not, and y is 6. These are all critical values because they cause both partial derivatives to be equal to 0. All right, check that out. None of them do we care about. Go ahead, Lee.
So it has to make both of them 0?
Yes,
Point?
yes. You have to make both equal to 0
point.
to make, yes, to give you a critical value. Yes. They both have to be equal to 0. And I'm telling you that at 0, 0, 9, 0, and 0, 9, both these partials are equal to 0. These are all critical values, none of which give us a maximum volume, however. The only one we care about would be the x's and y's that cause this and this to be equal to 0. Okay? Well, let's do it. Let's subtract first minus second to get 3. And if we do this minus this, it's this plus this. It's a negative 1x, negative 3/3 x. Okay. This minus this cancels out. This gives us x equals 3. If x is equal to 3, the y is equal to, here, put a 3 in here. You get 3 over 3 is 1. 2, y is 2. The z is equal to, go back to the z, which was equal to, way back here, z was 12 minus 4x over 3 minus 2y. The z is equal to, put a 3, 8, minus 4 is 4. So the z is 4. Okay. We get 3, 2, 4. Okay. 3, 2, 4 is our critical value. And we should check it with a second partial derivative test, and that's what we're going to do. But I do want to point this out. The 3 is 1/3 of the way to the limitation on x, to 9. The 2 is 1/3 of the way to the y-intercept of 6. And the 4 is 1/3 of the way to the z. It turns out, no matter what the intercepts are, no matter how crazy that shape is, how steep it comes down or how wide it goes out over there and narrow over here, it's always 1/3, 1/3, 1/3. Will maximize the volume of the inscribed rectangular solid, which to me is just mind-boggling. It always comes out to be 1/3, 1/3, 1/3, no matter what it is. So when they're equal, say 6, 6, 6, you're going to get the cube because it comes out 2, 2, 2. Okay? And then again, what you can do then is take this. Now the sphere question is a little bit more difficult because you're going to have to find that point where the sphere fits inside that tetrahedron, inscribed inside the tetrahedron. It can be done. And it's kind of interesting. You can find out where the two would be equal. And it's an interesting problem. Anyhow, this is always 1/3, 1/3, 1/3.
How
Yes?
would you go about the problem if you were trying to find the shape that we're fitting in without the intercepts? Like, what if it didn't have those intercepts? It was just like a shape.
Oh, like an arbitrarily selected shape?
Yeah.
I have no idea. That would be a difficult. That'd be a very. Then I think the answer is like the tetrahedron, fill up the shape. So you're telling me we don't necessarily have a plane.
Like, instead of having the intercepts be on the axes,
Yes.
the shape ends somewhere between the axes.
Shape ends somewhere in between them. I don't know, you'd have to show me.
Like it's just different coordinates.
Our thing, but
Yeah, like-
rotated.
Like, say we take like the X coordinate, we just like move it out and give it some like Y coordinate as well.
Ooh, it just depends.
Okay,
That would make it harder.
So there's 3 coordinates in space. Give it-
yeah, I'd have to see what you're talking about there. If you could come up with something.
I can try to draw something.
All right, draw.
Radius.
Draw. Let's see.
Like our figure, but rotated around the z-axis by pi over 4.
By pi over 4 around the z. So take this and move it that way by 45 degrees. And so you've got, instead of coming down like this,
No, you're.
you've got something else coming down over there. Well, I think that could be done, but I'm not sure his could be done. Because I'm not sure.
Like
How
something
would
like something like this, where instead of like it ending right there on
That's
the
what
plane, it just like sticks out a little bit, and you have the flat part. right
Now,
there.
are there restrictions on the shape that we can put inside that thing?
I don't know.
If there are no restrictions, I'd say fill up the space.
So well, I mean, like, what I'm really trying to get at here is, how would you go about this if you didn't have the shortcut to find the equation of the shape?
Oh, well,
The
the intercepts, if I didn't have the intercepts, but I knew we had a plane, okay? But, see, I'm gonna have to be given some information.
You just rotate your axis.
Yeah, or something like that. I'm gonna have to be given something that defines that plane coming down, or whatever it is that's coming down. If it is a plane, if you were to give me anything, not the intercepts necessarily, but 3 points on the plane, give me any 3 points on the plane, we could do the problem.
Because you just use a cross, like.
Yeah, then we'd have to do the vectors and cross them and find the normal, and then find the equation of the plane. We could do it, as long as I had a plane coming down. Even if I don't know the intercepts, but all I need are 3 points on the plane. That I could do. But I'm not sure if you're making them even more complicated. If it's a plane, I can do it. If it's something else, I'm not sure. That's my answer. Yeah. David?
Is this similar to how the Russians designed those cathedral buildings? Because the way they did that was they had a rectangular building coming up, and then they had to figure out, they had to do like a maximization problem where they had to figure out how big to make the sphere, because if it was too big, then it couldn't support, the building couldn't support it, and then it would come too far down into the thing, but if it was too small,
Okay.
it would,
It would fall through,
Yeah.
yeah, in effect, yeah. I don't know, but it's certainly possible. There's a sphere, you can find how much the sphere would dip into that.
That's what they did, I think.
Yeah.
Because they had issues with space.
Yeah, I think we could do that. Matter of fact, when we do the triple integrals, we could do something like that. We could take a sphere and intersect it with a plane and find the volume bounded by that plane in the sphere. That's kind of what you're talking about.
I'm
right
literally
there.
trying to fit a circle into a square hole.
Yeah, well, yeah, well, that's true. Yes. Oh, was that a question, Janice? No. You were just twirling that thing. Well, that's okay. All right. So anyhow, it turns out that it's always 1/3, 1/3, 1/3. That will maximize the volume of the rectangular solid in the sphere, no matter what the intercepts are, which is kind of interesting. But we should test and verify that what we have here is indeed a relative maximum. And let's do it. Let's prove it. Yeah, that's the spirit. That's the spirit. Let's prove it. So here we go. What the heck? I got a Z diagram on the other side. All right. So let's prove it. What we're going to do to prove it is take the second partial with respect to x. And we have our first partial, 12y minus 8xy over 3 minus 2y squared. The second partial of that with respect to x is going to be a negative 8y over 3. That's kind of nice. What I'm doing here is taking this. This is what we have. This is our first partial with respect to x. And now I'm going to take my second partial with respect to y. Here's the first partial with respect to y. The second partial with respect to y is negative 4x. That's nice. And we also need our mixed partial. We'll do xy, but you can do yx if you'd like. It's the same thing. Now, here's the partial with respect to x. I've got to take its partial with respect to y, and that will give me 12 minus 8x over 3 minus 4y. Okay. And then we're going to find d, which is second partial with respect to x, second partial with respect to y, minus the mixed partial squared. Here we go. Negative 8y over 3 times a negative 4x minus this partial square, 12 minus 8x over 3 minus 4y squared. So we end up with 32xy over 3 minus that thing's square. I'm going to need help on this. Shoot. 12 minus 8x over 3. Well, let's substitute in. Let's see if I need help. That's equal to x is 3 and y is 2. Oh, that's not bad. 3, 2 over 3. No, I don't need help on this. 8x is 3. Y is 2. Bless you. This is 64 minus, these cancel, 4 minus 8, negative 4 squared, 16. That's 48. Greater than 0, that's good. We don't have a saddle point, at least. And then what? Look at the second partial with respect to x. At this point, which is a negative 8y over 3, and the point in question is 3, 2, 4. Put the 2 in there, we get negative 16 thirds, which is less than 0. Second partial less than 0, think concave down. Think maximum, okay? And that's what we have, a relative maximum. We have solved the problem. What we will do is anchor this rectangular solid at the point 3, 2, 4. Put that rectangular solid in there. That is the rectangular solid of maximum volume that will fit inside that tetrahedron. Okay? And we are done. Cool. Any questions on that? So, I'll have to just go over it with Anthony there. I don't know why he was interested in that one so much. Do you know why?
He likes lobsters.
Good answer. All right, so tomorrow, no classes. Thursday, I've got one other max-min problem that we can do. At some point, I've got to go over this lab. I'm not sure what the lab is.
Let's just do it tomorrow.
Can we do a roadmap tomorrow?
A what? Roadmap tomorrow. Well, you'd have to come over my house. But that's okay. Then you get all rate. Yes.
No.
Yes.
How big is your house?
No.
Do we get paid for it?
Get
the roadmap.
Yeah, that's right.
You get paid in knowledge.
Google it. It's 50 cents an hour.
No, it's not due. The lab is not due until a week from Friday, so it's waiting. Thursday, I got one more problem to do, a pipeline problem. And then I'll probably show you the lab on Friday, and then review. I'll give you a roadmap on Friday or something. What's that? Oh, yeah. Oh, yeah. And